Which associated material talks about the Sears Tower? Just, you know, out of curiosity.
Say that again.
Which of our associated steel material talks about the Sears Tower?
None. Why, you have a question? You're interested in that?
No, for the quiz, you had a question about the Sears Tower.
Oh, there's a quiz. Okay. Yeah, I might have. I'd have to go back and look at that question. Is that
Yeah, me too.
which for the module one or for the module for tension
Module
member?
one. It's
Okay.
asking about percentage of steel saved as a result of revised specifications.
Oh, that was one of those videos that's linked in the in Canvas.
Oh, okay.
Yeah, I think there's a passing comment in one of those videos that says something to the effect of if the Sears Tower were redesigned now, there would be such and such percentage savings in steel.
Yeah. Okay.
Yeah,
What did you
yeah, I'm teaching on this computer, but the camera's over there, so that's kind of awkward. I don't like teaching from my office in general, but be that as it may. The there was another error too, another problem as well that a different student alerted me to concerning weathering steel and the change in designations from the 15th edition manual to the 16th edition manual. I'll touch on that tomorrow in beginning of class.
what did you make of that co-op research program? Like that
Well,
sounds like it could be helpful.
yeah, I don't know a whole lot about it, so that's something to look into at some point. Um, yeah, I don't know. A lot of the funding that comes from UC sources like that come with strings attached, and some of those
Yeah,
strings, yeah. And so there's been undergraduate research experiences, and that tends to be more work than it's worth.
sure.
It's interesting. This computer, I can't get the audio to go any louder, and it's not loud enough to suit me. I wonder why that is. Huh. Go back here and tinker with maybe it's Zoom. So the way audio goes through these speakers, it goes through computers now. There's like 15 different. Oh, that's it. Okay, I just found it. So Zoom had the audio turned down to like 20%. All right. Can you hear me? Okay, I guess I'm coming through all right. Or shoot, I've got a little nano microphone here. That's
I suppose you're usually in the confines of your home, aren't you?
yeah, and I have a nice Yeti there with some post processing on it. But this one, I bought this mic over the summer and it always sounds tinny. I can't get it to not sound tinny. And so it's been disappointing. Ben Carson.
I'm here.
All right, we're missing one. We'll give. I guess it's already a minute after. So, well, let's get started with the announcements. Right. So today is Tuesday, September 5th. Here's my schedule for this week. So office hours tomorrow afternoon, tomorrow after lunch, 12:30 to 2. I'll be here in my UC office. I'll also launch Zoom at the same time. Then the second Tuesday of the week, September 7th, that's going to be office hours 8:30 to 10, and then a live class session after that. Okay, we still don't have a TA for the class, and you guys have a homework due today. So if we don't get a TA for the class, then we'll probably keep the same syllabus with respect to how much points for the same grade distribution, how many points for homework, how many points for exams, that sort of thing. The big difference will be that if I end up grading your homework assignments, I won't go through and mark things up with a fine tooth comb. I'll probably just look them over to make sure you've done the assignments. And if you've made an honest attempt, then you get full credit. If it looks like a half-assed attempt, then yeah. So the amount of time that I have to spend on homework is literally about 30 minutes a week. It's just, financially speaking, it doesn't make sense for me to spend my time doing that. So the second homework on beam modeling is due on Tuesday of next week, also at 5 p.m. And so you guys should have everything you need to do the SAP 2000 analysis of that. And then after today, you should be able to do the first problem, which is visual analysis. So what we did last time was we went and modeled that beam from tutorial number 1 in SAP 2000. And so what I want to do today is go through that same tutorial and do the modeling in visual analysis instead. So let me open up the PDF tutorial so that we can work from that. Okay, and I'm going to work from my other computer. So let me stop sharing here. If I do that, there we go. It's funny, the stop sharing button is on the screen that I'm not sharing. Disabled screen sharing to all participants. All right, so here's visual analysis, and let me go ahead and create that beam that we were tinkering with last time. And so I don't think I saved that, regrettably. I wished I had, and I did not. So let's see, I had members. Let's go ahead and draw that first one. And now zoom over. There we go. Now we'll go back and draw that in again. So we have one member that goes from 0 to 60. See if I can get it right this time. Then the next member goes from 60 to 135. I'm going to leave it at 136 for the time being. And then it goes from 135, 60, gives me 195. Zoom out. I didn't zoom out far enough. You would think that they would make this more user friendly and you could actually drag past the edges of the window, but they don't allow you to do that. There we go. Now what I'll do is I'll window over these two nodes and I'll move them one to the left. Let's see. Move. And I'll move it 1 foot to the left. There we go. All right, so now they're where they need to be. I'll go ahead and window over that. I'll make that pinned. I'll window over these three. I'll make those, they don't have rollers, so I'll just, Y is all I need there. Okay, and then we went through and put dead load on these last time. What was the dead load? 1,450 pounds per foot, I think. So go to loading, apply member load. D, I don't want, let's see, uniform load in the Y direction, so minus 1.450. All right, so that basically gets us back to where we were. Let me go ahead and change the model from a space frame to a plane frame like that. So now the next step is that we want to add pins. We want to add cover plates to this model, and then we want to add pins to it as well. So we need to break the members 7.5 feet to the left and to the right of nodes B and C. So you can do the same thing in visual analysis that you do in SAP 2000. Over here, it's called split members instead of divide frames or edit frames. So you can go in here, I want to split that member, and you have different options. I can specify the lengths, I can specify the fractions, I can put an interior node and have it split it at that node. And so here I'm going to say segment 1 is going to be equal to 60 minus 7.5. Oops. And that gives me 52.5 feet. So you can see it added that node in there like that. I can do the same thing with this guy here. Split that member. That one I want it to be lengths. I want it to be 3 segments instead of just 2. So the first one I want to be 7.5 feet. And let's see. Then the next one I want to be 60 feet. And so I can split that member into 3 all in one operation. So that's a bit more convenient than what we had with SAP 2000. Then I can come into the last member, split that. I want it to be specific lengths. I want the first member to be 7.5 feet long. Right. So with that, then we can come in and select those members there. Forgot to hold down the control button. There we go. There's the control key. Now I can go over here and note that it automatically selected 6 nodes. I want to edit the 4 members though, not the 6 nodes. And so now we can go into the database shape and we can add in a standard parametric shape for those elements. And no, not standard parametric, custom blob. There we go. And so with the custom blob, we can actually go in and add in our section properties that we need. So if we go to the last page, you can see that we have a moment of inertia 23070. So I can come back here and say that the moment of inertia is 23070 and 23070. The moment of the cross-sectional area, the polar moment of inertia, etc., none of those matter for what we're doing. Just the moment of inertia now. We don't have an axial force on it, so the area doesn't matter. We don't have torsion on it, so J doesn't matter. We're not calculating stresses, so the section moduli don't matter now either. So we can come up here and put a name here. So I call it W36X231 with CP, and that would be great. Okay. One thing that visual analysis does better than SAP, even though this thing is set up to be working in feet units in my main window, when I go to put in section properties, visual analysis knows that I like to work in inch units instead. So it does a better job. And when you look up here at the top on your units, you can see USA mixed. And so it does a better job of anticipating what it is that we want when it comes to those units. Excuse me. All right. Then The next thing that we'll do is add in releases. So we need a set of pins at 15 feet to the right of B and 15 feet to the left of C. So I need to split that member again, and then I'll add the releases in. So I'm going to select this member. I'm going to go to split members. I want 3 segments with specific lengths. So here I'll type in. Too bad that it resets every time. It's too bad. So that's 3. That is going to be 7.5 there. This one is going to be, let's see, 60 minus 15, which I could do in my head. I can actually do that. And then that gives me that. Now I'll select this member here, go over to my model filter. I'll edit that member, and you can see there's an option for releases here. And I'll go ahead and release the strong axis moment M1 and the strong axis moment M2. And you can see that it puts those little circles in at the end of the member to indicate that there is some type of a release there. Okay, now I can do a preliminary analysis now to see if that works. All right, one issue found. So what's that? Let's click for a report. Creating a report. Okay, there's a huge stress in one of the members. So that's not a deal breaker for me. We didn't put in the proper S values, so my guess is that it probably calculated an erroneous value for that stress. So I'm not going to complain about that too much. Now we can come in here and shift and then drag a window, and we can go to member graphs, and we can look at the bending moment diagram and shear force diagram and such. All right, let's go back to the model view. I'll add in my truckload now. And so we wanted a truck with, let's see, we wanted the truck facing to the right, I think. It's up here in this paragraph in the first page, I think. HS20 truck facing to the right with the center axle and the midspan of BC. Center axle, midspan AB, right. So we can go ahead and add those in there as well. So one thing, in order to add those, we have to define new service cases. So I hit the load case manager. I come into service cases, and there's a button down here at the bottom, or a checkbox that allows us to show the empty cases. So it's only showing dead load now because everything else is empty. There's no loads associated with it. But if you check that box, then it already has predefined load cases for every load that it thinks you might want to put in there. So it has live load, it has live load on the roof, it has rain load, snow load, horizontal earth pressure, fluid loads. It has wind in the positive X direction, wind in the negative X direction, wind in the positive X and Y direction, wind in the positive X but negative Y. So it goes on and on. So these other ones all have 0 loads. But what I want to do is define 3 different load patterns for live. I want live load with the truck in the first span, live load with the truck in the second span, live load with the truck in the third span. So what you can do is create a new service case, and we can go in and call it HS20. I'll call it span AB, and that's going to be a live load. It needs to know what type of load it is so it can apply the correct load factors, load combinations, and such. Then down here, where do we want to include it in our analysis? Yes. Do we want to include it in our building load combinations? Probably not. And then there's a pattern ID, and we'll leave that alone for now. We'll come back and talk about that in a few days. No self-weight in that at all. All right, that should pop up here. Is it the bottom? Yep, there it is. So let me create a second one. We'll call that HS20 span BC. I'll do the same deal like that, and then we'll create a third one. HS, 20, span CD like that. All right, so now I have those 3 live load cases. And so when we define a load pattern in SAP 2000, the analogous situation here in visual analysis is a service case. let's go ahead and check this dead load. I can either double click on it or I can click on the modify button here. And when I did that, I didn't disable the automatic self-weight. So I want to change that so there's no automatic self-weight included. And so that goes away like that. All right, now let's go ahead and put point loads on here. So let's go ahead. I want this to be the HS20 applied to span AB. So I select that as my load case, and then I can go ahead and add the load. So I go to the loading tab, apply member loads, and then I want not a uniform load, but I want evenly spaced point loads. And so let's see, that member is now what? It's 60 feet minus 7.5. So that member is 52.5 feet long. And if I want the middle axle of the truck to be at mid span, that means I want the middle axle of the truck to be at 30 feet. So then subtract 14 from that. So I want the first load offset to be 16 feet. Then I want the loads to be spaced at 14. And I don't think that's going to work. If I go in and type minus 32, that's probably going to give me too many loads on that. Yeah, so then the front axle isn't 32 kips. So let me undo that. I hit Control Z. Let me go in and do member load again. I'm just going to go single point load. I'm going to go minus 32, and I want that to be 14 feet. Then I'm going to go in and do the same thing again. I'm going to add a single point load. I want the offset to be, I didn't want that to be 14. I wanted that to be 16 feet. Let me click on that load. Go over here. I can change that offset from 14 to 16. That moves that over. There we go. Now this next one, I want to be at 30 feet. That. And now I'll apply one more for the front axle. And this is going to be minus 8. And this is going to be 30 plus 14, so 44. There we go. So there's that truck. Then I can come in here and do this. That member has a length of 45 feet. So I'm going to apply my loads like this. So single point load, I need to go to different load service case. So span BC, there we go. I want minus 32. I want this to be at 22.5 minus 14. And there we go. Now it didn't show up. And so my first thought was, oh shit, what did I do wrong? But if I go up here to the ribbon, I'm showing the loads that are in service case HS20 span AB. So if I change this to span BC, then that load that I just added will show up. Let me go ahead and add another one. So this one's going to be at 22.5 feet, right at the center line. And then the last one is going to be at 22.5 feet plus 14. And this is going to be minus 8. There we go. Perfect. Now let me go over here. Somebody else joined or somebody dropped off? Sure. I got a text message when I look and see. All right. Let's go apply member load. This is span CD. I want minus 32 kips, and it would be 16 feet minus 7.5 feet. And it didn't show up again because I'm not showing the right case. There it is. Now, 2 more loads to go. Apply member load here. So this is going to be 30 feet minus 7.5. And then lastly, minus 8 at 30 plus 14 minus 7.5, 36.5. All right, so there's my cases. Let's go ahead and run the analysis. I'll probably get that same warning again about the stress. Let's close that up. And then we can go here and look at member graphs. So there's my dead load. I can look at live load there. I can look at live load in the middle span, and I can look at live load in the right span. I can also look at the load combinations. I told this program that I have dead load and live load, so it selected the load combinations that it thought were appropriate. But the problem is that it's working by default from the ASCE7 load combinations. It's not working from the ASHTO load combinations that we want. So let's go back to the model view. Let's go to my edit load case manager and look at the load combinations. Now, this is quite robust. It has a bunch of them built in, all a number of different versions of ASCE7, International Building Code combinations, but it doesn't have anything associated with ASHTO. So what I can do is I can deselect that, and then I get none of the default load combinations. And what I can do is create a factored combination. And so I can come in and call that ASHTO STR1, and then I can break it down like this, and I could say with the live load in span AB. And so I can put a factor on the dead load, 1.25, and then a factor on the live load, what was it, 1.75? Yeah, 1.75. And so this is going to be 1.75. And then if I want to, I can include impact here. So I can multiply by 1.33 for the impact factor. Then I can include the distribution factor. What was it? 0.979643, 0.9643. It won't let me put those in there. Okay. Let me just include this factor of 1.75 like that. Right. And then I can hit OK. And then I can create another factored combination. Let's spell ASHTO right this time. ASHTO strength 1, span BC, and factor 1.25 there. And for live load and span BC, 1.75 like that. And then the third one, finally, ASHTO strength 1, span CD. 1.25 and 1.75. All right, let me go correct that typo there. All right, and then close. Right, so now we can go back to the results view, and when we plot our graphs, we have not only the source loads, but we also have the load combinations as well. So there's a load combination of dead with the truck in the third span. All right, let's check over here for the chat. Anybody has any questions? All right, we all good so far? Okay, now in those loads, I screwed up. I didn't add in the self weight for, I didn't add in the impact factor or the distribution factor. So I can select those loads like that. The magnitude varies. So I can come down and number loads concentrated. I can come in here. Can't edit those though. I was wondering if I could, and I cannot. Okay. So what I can do is select them one at a time. Select that guy, and then I can come in here and type in times 1.33 times 0.9643, and that changes that magnitude. All right, and then can do that one at a time. It's not quite as convenient as it was in SAP, where we had that table, 0.96. Yeah, that gave me an error because of the K that's in there. All right, and then I'll just do this last load here, and then I'll let you guys do the rest of it by yourself. So let's try 1.23. That didn't work because of the K. All right, so there you go. So now the last question is, how do we do an envelope of those three? So you can come in here to load case manager again. And what you can do is advanced case, create envelope results. And there's a checkbox for that. And so if you do that, then we can come back to the results view and go to member graph. And whoops, I didn't select all the members. Damn, that's annoying. Supposed to be annoying, I guess. There we go. Now we go to member graph. And so we have all cases high extreme, which gives us an envelope there, and then all cases low extreme. So that's the an analog or the equivalent of the envelope in SAP 2000. Now I have an entire presentation on the load combinations. SAP 2000 is very robust. Visual analysis will do a lot for you, but that's a conversation for another day. So after you guys submit your next homework next Tuesday, the first beam, then we'll come back and look at some more load combination stuff and get a little bit more complicated with that. But for right now, I want to shift gears a little bit and show you a couple of things in the background. The first thing is that we had a discussion earlier on that said that it's okay to put a release to the right of this node. It's okay to put a release to the left of that node, but if you put a release on both sides of that node, that creates a problem. And I want to show you that. So I'm going to select this member here, and I'm going to go in and release the strong axis moment at M2. So now what I have is a moment release on both sides of that node. And if I go into the results view now, it gives me an error here. And this is a different type of notification than the one we got before. The one we got before was a warning. This one is a flat out error. And it says that the model is unstable and cannot be analyzed. We have attempted to show you the unstable mechanism by doing a modal analysis. You can use the mode shape to establish where you need to add structural support. And so by adding too many releases to the model, I've created a situation where there's a numerical instability. And so that's its best guess at how to make it stable. So that is a no-no, and that's a problem. Now we can include the release to the left of that node. So if I go into this member and remove that first release, this should run just fine. All right, now note that this status window is yellow now instead of red. So it's giving us a warning, but not an error. And it's still giving us the results that we had. And so that's okay. You can either put the release on the left of the node to the right of the node, but you can't put it on both sides of the node. Now, with that in mind, let me Alt tab over here to SAP 2000. And I have the window open from the model that we created last Thursday. And so you can see the releases here. I have this middle beam release, just like I did in visual analysis. Let me go in and select that member and add a release to the right end of that member. So I'm going to go in and add a release, major axis moment at the end of that member. I go in and hit apply. I wait a conspicuously long time. There we go. Now, so I have a release on both sides of that member. If I go in and analyze this now, it gives me results. It gives me a warning message, but it goes and calculates a bending moment diagram. In fact, I could come up here and look at the bending moment diagram for just about any case I want, right? So I can look at the live load in span 1. So let's read this warning message. And this would be a great case if I could zoom in, but I can't. It says, warning, the structure is unstable or ill conditioned. Check the structure carefully for inadequate support conditions, blah, 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 blah. But the difference between that message in SAP 2000 and the message in visual analysis is that SAP 2000 tried to correct the error, and it went on and did the analysis after it corrected the error. Now, that might sound like a great feature to a layperson, but to an academic like me, that's a very scary feature because it's really easy to click OK on that warning message and just ignore it. And then what you're doing is relying on the idea that SAP knew how to correct the model and that it did it right. I would actually rather have it say, hey, there's something wrong here. You got to go figure out what's wrong, correct that, and then we'll give you results. But a lot of the programmers that are behind these pieces of software, they look at it differently. So if you're writing a piece of software and it pops up and gives somebody an error, the user might think, oh, the software is screwed up. I'm going to go use a different package. So the programmers for this software, they tend to want to give you results at all costs. So you have to be very careful about that. And in fact, in this case, SAP 2000 probably made the correct correction to give me some results, and it probably would have worked out fine, but that's not always the case. So let me go ahead and unlock this model. I'm going to go back and I'm going to zoom out again first thing. Boy, this just runs so slow when I'm streaming. Let me zoom extents, restore full view. There we go. Let's remove that release. So I added it in, now I'm removing it. And so now I'm back to a good stable model. If I run this model now, then it just pops up and gives me results straight away, right? So you should get in the habit, even if you don't get a warning message that pops up, at looking at the log file. And so if you go into the Analyze menu after you run your analysis, you can actually show the last run details, and it'll pop up this window, and it'll tell you, it creates a log file that you can go in and look at, right? And it'll tell you how many degrees of freedom were in it. It'll tell you that it did the analysis correctly. And if there were any warnings that it created, here's the analysis messages, and that's where they would pop up. And so there aren't any warnings, there aren't any errors. So then you can go through and have more confidence in your model, right? So there's a whole lecture to be had on validating the results of your model. You don't want to just press the analyze button and then take the results and go and design your structure. You need to do some model validation to make sure that you haven't screwed up things. The first step of that model validation is to review the analysis messages here and in visual analysis. All right, now I have a to-do list of things I want to tell you guys about. Questions at this point? I'll take a drink to try and keep my voice from going away. All right.
I actually have a question here. If
Sure,
we
go ahead.
were to add point loads, could we also just add nodes at those points and then add node loads? Would there be a difference in that?
The short answer is yes, you can, but you have to do a few things in order to make that work. If we just add a node, you have to connect that node to the members. And so SAP is pretty smart about doing that. It'll detect that there's a node there and it'll split the member and connect the member automatically. Visual analysis is less smart when it comes to that. So if we go back here, let me use a new case and we'll just call it L. So let me go to structure. I can create a node and I think I can click here. Nope, I can't. All right, so let's call it, I know your name's not Ben, but it's funny to me. So let's put that at X equals what? Let's say 37.5 feet and hit OK. All right, so it created that node. Now we can come up here for loading. We can apply a nodal load there. Let's put minus 500 kips, and we're going to put it in the live load case. Just the, oops, I believe that's not nice. Like that, and then I'll hit OK. All right, now let's look at that load case there. All right, so, So if we go to the results view, it gave me an issue here. And so it automatically detected that node and said, yep, okay. So it was idiot proof enough. So I was hoping that it wouldn't do that. That was just a node that wasn't connected to those members. It actually went in and connected it to the members automatically. Not all packages are going to do that for you, so you have to be careful. You can, yeah, but you can do that if we're doing, yeah. So the short answer is yes. Carson. Good question. Any others? Okay, I'm getting blitzed by text messages. I'm not sure if that one's probably family. Yeah, it's funny. They have a sixth sense of when I'm in class, and then they start hammering me with text messages. This one, is that you, Joe? No, that's not you. All right, let's go back to SAP 2000. I want to show you a couple other things here. I'm going to create a new model, and instead of using the grid template, you can actually go in and use this beam template instead. And you can use this with a span length of say 60 feet, and or you could go in and use a custom grid. So this is pretty handy. So we could go in here and say I want the grid line A to be at 0. I want grid line B to be at 60 feet. And then here I'm going to type in 60 plus 75. Here I'm going to type in 135 plus 60. And so you can go through that. And then let's see, here we could go in and import a property. That's an I shape. So this is AISC 15 and 236, 231. Right, hit that and then hit OK. Yes, I want restraints. And so then it goes through and it creates that model for you. So that template is pretty handy. If you know what you're doing, you can you can create a model quicker with the template. But you have to be careful. Like anything else, if you try and take shortcuts, sometimes you run off track. Another thing that we can do, let me go here to define section properties. We go to frame sections. We when we added the cover plates, we went in and added a new member, and then we went to other, and we went to general. And so here is where we typed in the value for the moment of inertia, and that's all well and good. But there's a couple more creative ways of doing that. We can hit add new property, go to other, and then we can use the section designer. And in here, this launches like a third world CAD program that lets you actually draw in the plates that represent. I'm sorry, is that not politically correct? Usually that's when people start laughing, is when I say something. So a 1990s CAD program that lets you draw in the cross section. And so this is kind of handy because you can have a section that's composite made up of concrete and steel. You can put in, a steel girder with different top flange, bottom flange, or whatever. But if you're used to using AutoCAD, this is going to be like pulling teeth because it's really, really, really rudimentary. But it works. It works well. I was telling somebody last week that I use this sometimes if I get a cross section and I need to calculate polar moment of inertia or something goofy like that. Then this is a great way of checking those calculations. All right, so that's another alternative. In this case, there's actually one that's a little bit more dynamic. If we go back here to built up steel, there's actually a rubric or a template here for a cover plated I-shaped section. And so you can come in here and specify what's the base I-shaped section. You can include a top cover plate, a bottom cover plate. These units look strange because I'm in feet units. So let me cancel out of that and go to inch units. Go back. Section properties, frame sections, add property, cover plated steel. And right, so now we've got grade 50 steel. You can override it with a different grade of steel for the top flange. The cover plates are width and thickness. And so this would be a far superior method of putting that cover plated section in than just using the moment of inertia, because then this is going to calculate the appropriate cross-sectional area, the appropriate polar moment of inertia. It's going to calculate the appropriate section moduli, so the stresses are calculated correctly, et cetera, et cetera. So that's pretty handy too. All right. Then the last thing that I'll show you about this, let me launch an editor here, file manager rather. I think I put this in a temporary directory and beam in class. All right, so here is that beam. So it created the SDB file. and SDB is the SAP database. So that's the actual input file from this guy. And when you run the analysis, it creates all these other files as well. And so there is one here that's called a $2K file. And that creates kind of like a hidden file. If an abbreviation for SAP 2000 would be S2K. It puts a $sign there instead of an S. If you open that file up using a text editor, I'm going to open it using TextPad. Then what that does is it gives you a text description of everything that's in your finite element model, everything that's in your computer model. So it gives the coordinates of the grid lines, it gives the coordinates of the nodes, it gives whether the nodes are restrained or not, it gives the load case definitions, it gives the load pattern definitions, it gives the load combination definitions. And so for the most of you guys, this will seem rather archaic, that why in the world would I want to do this with a text editor if I've got a graphics user interface? But if you're checking the model and you want to be specific about nodal locations and things of that nature, then this is really nice because you can go in and check all of that. And in fact, if you're so inclined, you can actually edit this file and edit your model. You can actually go into this and let's see, what could I change? I could change a nodal location, for example, and then I can re-import the file and have that change implemented automatically. So let's see, here we go. The F5 is fine. Those are the joints. That's the frame connectivity. Coordinate system. I'm looking for the nodal locations, joint location. Here we go. Yeah, so here's the joint location. So joint number 11 is currently at X equals 120. Node number 6 is currently at node number X equals 142.5. I wonder how it got there. That's interesting. Here's one at 135. So let's go ahead and we could change these numbers. So I could put in a Y value. Let's put in a Y value of, say, 60. And then I'll save this as a different file name. I'll say save as, call it goofy dot, I'll call it S2K instead of $2K. All right, so I just changed that text file. Now what I can do is come up here to, I think it's file, import, and I want to import an S2K text file. And I want to create a new model, go to OK. No, I don't want to save this one. And so then I'm going to navigate to that file, temp, beam in class, goofy S2K. And it runs through that text file. It gives me a couple of warnings in here. Actually, no warnings, no errors, no informational messages. And yeah, so there's my beam with that goofy Y location. So if you were so inclined, you could actually create the entire model in a text editor and then import it into SAP 2000. And Carson, you're saying no, you wouldn't do that, or you're talking to somebody else?
No, I definitely would not do that.
Okay. Well, there's a time and a place for it. You could, yeah, but knowing that it's an option is a good thing. All right. Now let's see. Let me go back to the original model that we were working on. That was XYZ SDB. No, I don't want to save changes to this one. All right, so here's that original model. And note that it's still locked, right? I still have analysis results that are associated with this. We go back here, look at all these files, right? If I unlock this model and then go back to this directory, most of those files have gone away. And so most of those files are associated with the analysis that was conducted on this model. I think this log file is a text file, so I can go in and open that up. this actually gives you the same messages that you got by going to last analysis results, right? And so it tells you the number of joints, the number of degrees of freedom, and all that. And then here's an out file. I don't think that's a text file. I'm going to try and open it anyway. So yeah, okay. So it is an out file. It gives you the number. Yeah. So there's a lot of behind the scenes things in SAF 2000. If you look at visual analysis, none of this exists there. There's one VAP file, visual analysis project, and it's all buried in that one file. When you go and do an analysis with visual analysis, it probably creates some scratch files, but it doesn't let you see them. It puts them in some place where you'll never find them. And all the results are buried in that VAP file. So visual analysis is a newer program, so newer programming protocols. SAF 2000 is an older program, was written back in the 80s. And so, you know, the heritage of that program is reflected in the approach that it uses here. Okay, and depending on which packages you guys are using, some of them might take an approach like this. Some of them might be more like visual analysis. I know if you use like RAM elements or RAM structural systems, it's old school like this. It'll actually launch different programs to do an analysis of the beams and then to do an analysis of the columns. And it would be archaic by your standards as younger engineers. But anyways, all right. All that being said, what I wanted to do next was to go back and spend a few minutes talking about local and global coordinate systems. So I'm going to come over to the other computer, and even though I'm not at home, I should still be able to sketch over here. I've got my Microsoft Surface. So okay, great. And let me try the pen. Yeah, okay. All right, so I want to spend a few minutes talking about local and global coordinates, and that'll probably be the end of the time. I posted 2 more tutorials for trusses, but we're not going to get to those today, obviously. So, all right, so you guys are all familiar with a coordinate system. And so I've got a general member here. It must be a flexural member, a beam member, because it has end moments involved with it. That member is oriented in an XY coordinate system. So we have the X coordinate here, the Y coordinate there. And so at each end of the member, I have a displacement in the X, a displacement in the Y, and a rotation about an axis parallel to the Z axis. So I have another displacement Y, a displacement X, and a rotation theta about the Z axis. Now, just because we have a coordinate system X and Y here, that isn't necessarily the only coordinate system we have in our model. In fact, depending on the package you're using, you're going to have at least one coordinate system associated with every element in the model and probably with every object in the model. In SAF 2000, for example, there's a local coordinate system for every frame object. There's for every node and for every constraint, there's another local coordinate system for that. And so there are multiple coordinate systems that are all acting in concert with each other to do the analysis. So you could have the same member. This member here is the same as this member here, but we can characterize the displacements in 2 different coordinate systems. There's the structure global coordinate system, capital X, capital Y. But then there's also a member local coordinate system like this that would be characterized with a lowercase x and a lowercase y. So you can have the displacements either relative to the global coordinate system like that or relative to the local coordinate system like that. And understanding that there are multiple coordinate systems is important because in a lot of cases, when we go and create our model, we're specifying x, y, z locations in the global coordinate system. But then when we go in and put loads on, sometimes we want the loads in the global coordinate system, sometimes we want them in the local coordinate system. but when the programs spit out results, they almost always spit out displacements in the global coordinate system, but they almost always spit out member forces in the local coordinate system. And so understanding first of all, that there are multiple coordinate systems, and then how they interact with each other is important. So if we look at visual analysis, for example, it defines its axes like this. The x-axis is along the length of the member, the y-axis is vertical, parallel to the web or in the plane of the web, and then the z-axis is perpendicular to that. And then if we go in and look at the output, this defines the bending moments that it's outputting for us. So it doesn't matter how that member is oriented in space, you're always going to get a member results, M sub Z or M sub Y, that are about the local coordinate system for that member. And then Joe asked, I think in the second class, what about rotating the member about an axis? And that's the beta angle that I was talking about when he asked that question. And in visual analysis, you set that by going to the project manager, and then you have an option down here that lets you specify that. So in SAP 2000, there are also local member coordinate systems, but they're a little bit different, and they're going to be different in just about every package you go to. That's probably one of the first things you want to look up is how does it spit out results? What's the sign convention? What's the coordinate system that it's using? And when you look at a frame object or a member in SAP 2000, it doesn't deal with a X, Y, and Z coordinate system for the member. It deals with 1, 2, and 3 axes. So in this case, when we look at our bending moment, we put our thumb in the direction of the 3 axis, and the moment that results is the strong axis moment. So that's going to be M33. If we put our thumb in the 2 direction, this is going to be M22. So it works out that M33 is a strong axis moment, M22 is a weak axis moment. And yes, Carson, I saw you just use your thumb. It's okay. There's nothing wrong with that. And so then V2 is our strong axis shear. And then at the other end of the member, it's reversed, but it's about the same. And we also have the beta angle in SAP 2000, and it works basically the same. So if you go to the SAP 2000 menus or manuals rather, and you know, there's thousands of pages of manuals for SAP 2000. You can actually look up the default local axis definition, and this is nice to know. It says that the local 1 axis is always the longitudinal axis of the member, taken as positive if you go from the ith end to the jth end, from the first end to the second end, or from the beginning of the member to the end of the member. This axis is always located at the centroid of the cross section and connects node I to node J. Then the local 2 axis is taken upwards in the positive Z sense, unless the element is vertical. If the element is vertical, then the element is parallel to the Z-axis, and then that definition blows up. In that case, if the element is vertical, then the positive 2 axis is in the positive X direction instead. And so if we look at some examples out of that, here is a member that is parallel to the Y-axis. So you can see the ith end and the jth end. The ith end would be the beginning of the member, and the jth end would be the end of the member. So when the person running the program created this member, they dragged that member from the ith end to the jth end. Then they created a beta angle of 90 degrees, and so that's how the member is oriented. All right, here's a couple of cases where the member is vertical. In the case on the left, they dragged it from the bottom to the top. So the 1 axis goes from the bottom to the top, from the ith node to the jth node. And in that case, the 2 axis would by default be parallel to the X axis, but they've included a beta angle of 90 degrees. So then that rotated the member 90 degrees. And so the 2 axis is now parallel to the Y axis instead of parallel to the X axis. And then over there on the right, you can see a different case. In this case, they dragged the member from the top to the bottom. So the beginning of the member is at the top and the end of the member is at the bottom. They included a beta angle of 30 degrees, so that rotated the member the opposite way. So you're always rotating about the 1 axis. So in the case on the left, your thumb would be pointing upwards. In the case on the right, your thumb would be pointing downwards. So that defines the positive sense of the beta angle. Okay, now if you're only working in 2 dimensions, like we have been so far, this is all almost moot, not quite, but almost. It's when you get into 3 dimensions that this gets quite confusing. All right, so then here's the sign convention for a positive axial force P and a positive torque T. If you look at strong axis bending and shear, here's the sign conventions for that. So you're looking at M22 and I'm sorry, M33 and V22. And then you could look at weak axis bending and shear, and you're looking at M22 and V33. All right, and then so the beta angles are used to modify. We've already talked about that, so you can designate that angle from the default. All right, now when you go in and look at member loads, you have to be careful about these because you can specify member loads to be either in the global coordinate system or in the local coordinate system. So if we come in with a W, and let's say W is equal to 800 pounds per linear foot, and we want it to be in the global Y direction, so I've got a capital Y there, then what's going to happen is if you specify that load on this member, that load is going to be applied like that. Okay. Now, if we go to the next slide, if you come in here with a W equal to 800 pounds per linear foot, and you want, and you want that to be applied in the local Y direction, then what it'll do is it'll come in and apply that load like this. And so the terminology is a little bit different from one program to another. If you go in the SAP 2000, it'll probably tell you that you're applying the load in the member 2 direction. If you go into visual analysis, it'll tell you you're applying it in the shear Y direction. So the terminology is a little bit different from one program to another, but I want you guys to be cognizant of the fact that some of these loads are applied in the local direction, some of them are applied in the global direction, and in the case of SAP 2000, it offers a third case. It says apply it in the gravity direction, which is the negative Z direction. So that's like I don't know, like a nuclear option, I guess. You don't even need the negative sign in that case. And then there's the idea of projected loads, and I alluded to this a little bit the other day. If we look at projected loads, so we could have a case of a projected load in one case over here on the left. So this would be a case where that load is applied like this, and the load is applied to the horizontal projection of the member. So this would be projected, and over here would be the alternative where it's not projected. And that difference can be significant in some cases. And if you're familiar with snow loading, we usually apply the snow load to the projected length of the member and not the actual length. All right, so that brings us to the end of the hour. The timing actually worked out pretty good. I'm pretty happy about that. So when we come back on Thursday, I'm going to work through those 2 truss tutorials rather quickly and show you how to model a truss. Those are labeled tutorial number 4 because we still have some more stuff to do with the beams. We're going to go back and revisit those beams again and do some more sophisticated stuff with load combinations. And then we're going to apply a moving load. So instead of having the truck in one position in each span, we're going to say, I want this truck to move across the bridge from one end to the other and give me the maximum values. And so we'll revisit that later on. That's just, some of you might be wondering why we're jumping from tutorial 2 to tutorial 4, and that's why. All right, so I'll stick around for a couple minutes to answer questions. Otherwise, I'm going to bug out and head back to Fairfield. But I'm available in office hours tomorrow at 12:30. Otherwise, Thursday morning at 8:30, or I'll see you in class on Thursday. All right, so with that, take care. Have a nice day.